And there we go. Welcome again to today's webinar. This webinar is going to be recorded. You'll automatically get a link to today's presentation and the slides as well. Thanks for joining. This webinar is brought to you by the Penn State College of Engineering and the NACK Center there with support from the National Science Foundation. This webinar is hosted by ATE Central. ATE Central acts as an information hub for the National Science Foundation's ATE grantee community. You can find out more about ATE Central and all of the webinars they host by going to atecentral.net/webinars. Today it's my privilege to introduce our panelists and our moderator today. Let's start with our moderator. Let me move that slide back one more. Thank you. Let's start with our moderator, Robert Ehrmann. Bob, you're the Managing Director of the NACK Network at Penn State. Please come along and come on and say hello to everyone.
Hello, everyone. I really appreciate you being here today. Hopefully this is a very worthwhile topic for you. We're really excited to have our friends from Columbia University here for today's webinar, and we'll be periodically, I'll be periodically be joining Mike in, but he's the main moderator here. I'm just his assistant for today. You might call me the color commentator. So thank you, Mike, and thank you, Dr. Ariel Sternberg and Dr. Zangiabadi.
Thanks, Bob. That's your audio levels sound really good, so we're looking forward to today's presentation. Let me now introduce our first presenter, Dr. Amir Zangiabadi. Amir, thanks for joining us today. How long have you been at Columbia?
Hello, Mike, and hello, everybody. So it's been a year, more than a year, actually. So I joined here as a postdoctoral researcher. So I was collaborating with several projects and several professors, and then it was a matter of luck. So I joined the Colombian Nano Initiative, and now I'm working with Nava, and now she's sitting next to me.
Good. Well, thank you very much for all the work that both you and she have done on this presentation today as we've gotten ready. So we'll have you go on to mute and ask Nava to come on. Dr. Ariel Sternberg, welcome today. Say hello to everyone.
Hi. Hello. I'm very happy to be here.
Excellent. And also, may I ask you the same question? How long have you been at Columbia? A couple years as well, I think.
A little over 2 years, yes.
Good, good. Nava, you're our lead presenter. Why don't you go ahead and take us forward into the presentation and click onto that next slide.
Okay. Okay. So thank you, everyone, for joining, and thank you, Mike, for the introduction. We are very happy to be here. This webinar objectives are to give you a little bit of overview of our lab, Columbia Nano Initiative, to talk a little bit about the fields of the various fields of research that are here at CNI, a very short and quick overview of the capabilities of research that we have, and then we'll go deeper into electron microscopy, which is Dr. Zangiabadi's expertise. And he's also going to give you examples from fascinating research projects that researchers are doing here at Columbia. So, sorry. Okay. Yes. So CNI, Columbia Nano Initiative, is an umbrella department for interdisciplinary research in nanoscience and nanotechnology. It means that the PIs that belong to CNI also belong to the home department, which is typically either in the School of Engineering or the Arts and Sciences. Columbia Nano Initiative was founded in 2014 between these two schools, and it consists of an administrative branch that handles grants and the finances of CNI, and the shared labs that both Amir and me belong to. And we supply now research services and access to equipment to over 100 research groups within Columbia. There are many researchers coming from outside of Colombia, other academic institutes, and also some industrial companies. So I mentioned the various research projects. I'm just going to name a few of the main ones. We have several groups working on silicon photonics, electro-optical devices using silicon micro and nano fabrication techniques. We have groups working on super atoms, which are clusters of atoms in specific class structure and composition, to create new materials that have new properties. To study them, we have groups studying 2D materials, materials that are very thin, made of several atomic layers, such as graphene. This is the most famous one. We have groups working on bioelectronics, using electronics for biological applications, for neuroscience. I'm going to talk a little bit about that soon. We also have groups working on creating non-conventional electronics, such as plastics, flexible screens, and all these applications. So one very important example is the Lipson group, Professor Michael Lipson. The group is working on silicon photonics. So silicon micro and nano fabrication techniques have been known very well and very well studied for CMOS and microelectronics. And Professor Lipson and her group are using them for optics and optoelectronics devices in a really wide range of applications. They're working on optical elements such as amplifier using nonlinear optics. They're using optical forces to actually create mechanical movements, mechanical displacements. They're using silicon photonics to create probes that are cheap and less invasive for neuroscience, developing on-chip biosensors to analyze bacteria, enzymes, and very other interesting applications. You can read about it more in Professor Lipson's website. I added the link here. Another group is Professor Ken Shepard. His group is working mainly on bioelectronics. They actually developed a prototype to measure signals from the brain. Again, the challenge is to be as less invasive as possible because this is the brain, but then to use the knowledge that has been accumulated for so many years in microelectronics and fabrication for those applications, and to basically create the interface between the biology and the electronics. Again, you can read more about it on the Shepard's group website. So this research and a lot of other research is made possible partly because of our labs, the shared labs, that consist of 3 types of labs. The clean room, we have a micro and nano fabrication facility here at Columbia. We have a materials characterization lab, and then we have the electron microscopy lab that Amir is the director of. As I mentioned, we have over 100 research groups. We have about 400 users using our equipment, and we welcome very much external users. We have an external user program, so if you want to come and use our labs, you are more than welcome. The labs are operated by dedicated technical staff, full-time, working here. The staff is managing the labs, they're operating the equipment, we train students, we fix equipment problems, we also help develop process recipes and support research questions. So a little bit to go inside the various labs. So I mentioned the clean room. So a clean room is basically an environmentally controlled lab. We have we finished recently to renovate and expand our clean room. It's 5,000 square feet in the 10th floor of a building in Manhattan. That was very challenging. Basically, the air inside the clean room is filtered. We have class specifications for that. The clean room is class 1,000 to 10,000. We have very tight controlled temperature and humidity, so people can reproduce the same processes over and over again with a high level of reliability. So this all is made possible due to very complicated supporting systems, air handling units. We have a central cooling system for all our equipment. We have dehumidifier, cleansing generator, and of course we have safety systems because the clean room has, by its nature, some dangerous chemicals and materials in it. So a little bit of overview on what we do. So inside the clean room, if I were to put this in very simple terms, we either add material to a sample or we remove material to a sample. So this is and we also control the areas where the material will be added or removed. So the way to control where we add the material or remove the material is by photolithography. We also have electron lithography, EBIM lithography. We have several pieces of equipment related to photolithography. We have two mask aligners, we have several spinners, we have a mask writer. And then after we create the pattern from the photoresist, we can etch the layers, the material. We can remove material using wet chemicals, wet etch, or dry etch using plasma. We have several reactors, plasma reactors that can etch and remove materials. We have several ways to deposit layers. Sputtering systems, we have EBIM evaporation. We can also grow very thin and very high quality film, LPCVD, low pressure chemical vapor deposition from gas source. We can grow silicon oxide, silicon nitride, silicon carbide, and perform some heat treatments to layers. And after the device is created, usually the researcher needs to connect to the outside world, to connect it to power, to connect it to sensors. So these connections are made in the back-end area where we can planarize devices, we can planarize layer with chemical mechanical polishing, we can dice chips, or we can connect them with wire bonders. So the materials characterization lab, that's the second lab that we have, offers a really large variety of characterization techniques. Users can learn almost anything they want on the materials and samples. I'll give you the main examples. Surface analysis. You can learn about chemical composition on the surface to learn which elements you have on your material. You can scan the surface, get a topography map, the roughness. You can learn how the material is bonded, how elements are bonded within your layer, or what surface area the molecule has. We have two X-ray diffractometers for single crystal and for powder analysis. You can learn about the crystallographic, the way the material is built, is ordered and organized, the orientation and which phases exist. We have DLS, data potential. You can also measure particles in suspension. If you have suspension of particles inside a liquid, you can measure the size distribution. You can also study polymers and in different solvents and temperatures, as well as optical and magnetical properties. We can measure refractive index. We can measure thin film thickness using the ellipsometer, magnetic properties, and optical properties, absorption and refractance. In addition to all the characterization techniques, we also have a stacking station for 2D material device fabrication. Researchers use this protected environment. It's a glove box with nitrogen environment inside. So the moisture and the oxygen levels inside the glove box are controlled. And users can, if you can see in the picture, users can put their hands inside the gloves and work with create the device, fabricate their device very gently without exposing it to the outside air. And then you can protect it before you take it out. I'll give a brief introduction on the electron microscopy lab, and then I'll clear the stage for the most interesting stuff that Amir is going to talk about. We have a large variety of sample preparation techniques here that are not shown on this slide. In addition, we have 3 electron microscopes. One is inside the clean room to allow study of the actual devices and layers while you're fabricating your device. We also have another SEM outside, scanning electron microscopy, and then we have the TEM, which Amir is going to talk more about. So with that, I'll conclude my part, unless there are questions, and before we move to Amir.
Yes, we do have several questions for you, Nava. One was answered by Dr. Zangiabadi, the one about superatoms there. But do you have any spin on superatoms there to add?
I think his response is perfect. It's basically the way the atoms are ordered can create different and new properties, desired properties for the material. So if you think about it, it's similar in a way to if you have gas phase, solid phase, and liquid phase. It's the same material, but the atoms are ordered in a different way. You have totally different properties. So superatoms is in a way controlling that with not just one type of atom, but a little more than that, and creating these big, gigantic clusters of atoms that are organized in a very specific way from several elements, and they have interesting properties.
Thank you, thank you. It seems to me from the questions there are a lot of people here who are very impressed with your clean room and perhaps jealous because it looks like very late model stuff that's out there, and it's quite impressive. But there were some logistics questions around it. One of them was, do you have like what's the size of your clean room was one that I can pick out there, the size of your clean room and your characterization
So
space.
the clean room is 5,000 square feet. Characterization space is a little smaller than that. I want to say about 2,000 square feet altogether. The clean room is recently expanded, so it used to be smaller, but it's expanded as part of the renovation. So I think you mentioned class of between 1,000 and 10,000. So the little area is cleaner. We have also 10,000, class 10,000 areas.
Okay, great. So like, who uses it? Do you use external users, industry users? Do you have any students, graduates, undergraduates? How does that work?
So mostly graduate students. For undergrads, we require, because of safety, we require supervision, so that's a little more complicated. But for graduate students, definitely. And external users, we have our external users program, so it is used by companies. We have several companies that are working in the clean room. We have users coming from a different university to use equipment that they don't have in their own university, so we have also external academia. We are open for anybody who is interested in. We have a lot of information on our website. At the last slide after Amir's presentation, we have a link to our website. So everybody is welcome to go in and read about us, get some more information about our access protocol, about our external user program. So definitely everybody's welcome. And of course, our emails are also the last slide. Feel free to email me with questions. I'll be happy to answer anything.
Fantastic. I think, Mike, unless there are other questions, we're probably ready to transition to the Dr. Zangiabadi. So
there's just one brief one. We just love superatoms here in this group. Can we say, you can see the question, can we say that a superatom is a nanoparticle? Is that correct, Nava or Amir?
Yes,
Nava.
We can say that. Yeah, in terms of size, you mean, yes, it can get to a nanoparticle.
I know in our classes we don't even talk about superatoms yet, so I'm going to start thinking about how to include that into our presentation. So thanks for the information. Let's go ahead. Nava, okay. Thank you. Would you go? Good. There's one more question about remote operation of the equipment. Let's deal with that a little bit later in the presentation as Amir gets started. So Nava, will you go on to mute, and then we'll ask Amir to unmute and take us forward in the presentation.
Thank you.
Okay. Hello again, everybody, and thank you, Mike. And thank you, Nava, for the introduction and covering the first slide for electron microscopy. That I'm managing the lab for electron microscopy labs, TEM and SEM. I would like to mention about the image in the middle, the TEM, the Talos TEM that installed almost recent, like 2 years ago, like pretty functional from 2 years ago, and it's one of the state-of-the-art instrument that FER or Thermo Fisher have, and I know that Penn State also have one same instrument, and they are pretty good on elemental mapping with their 4 silicon drift detectors. And they're very good for high-resolution imaging on TM mode and high-resolution STEM mode. Okay, so the next slide. I would like to talk in just 2 slides about type of microscopes and what electron microscope is. So we're normally interested to observe objects in different sizes. From very small objects like atoms, we can go larger to like bacterium, like objects that we can see by eyes, and even we can see objects that we have to use telescope. We have to use different waves or different wavelength of waves. So in any of these, we are using some sort of waves or something that we can use it to observe objects. So the difference is that when we are looking from the left to right, we are also decreasing the wavelength of the wave that we are using for observation. So from the light microscope to electron microscope, we're using a smaller wavelength of electron wave, and there are equations that show that by lowering the wavelength, we can observe smaller objects, or on the other word, higher resolution. So when you look at this diagram, you see on the very right edge, you have X-rays and gamma ray. So I have a very quick question from our audience. I would be happy if they have the answer. Why we don't have X-ray microscope or gamma ray if you're having the even smaller wavelength of those? If you know the answer, just leave the comments. I'll get back to it. So electron microscope is very interesting in the way that it's very, very similar to optical microscope. The microscope that we see in every lab, like the image on the left, it's small, you can hold it, and it's not very expensive. They're very cheap. And you see on the right side a giant TEM or electron microscope in Japan. It's made by Hitachi, and it's like a two-floor building instrument. And you can compare the size of it with the operator standing next to it. But when you look at the diagram, it's pretty much the system is similar. Instead of glass lenses, you're using electromagnetic lenses. Instead of light source, you're using a gun that produces electrons instead of photons. And at the end, instead of looking at the image by eyes, you're looking at by a camera. So the principle is very similar. I'm going to show you very quick results of the instrument that we have at Columbia University. What we are looking at, these are actually atom columns. This is a silicon that is oriented in 110 direction. So with the capability of STEM, or scanning transmission electron microscopy, you're scanning like a TV, like an old CRT TV, and we are looking, we are kind of seeing atoms. And when we are looking at the image on the bottom left, that's a simulation that we normally need a simulation beside the high resolution images to compare our results. So next, I'm going to talk about quickly on the specimen preparation. So I'm jumping to the specimen preparation because it's a very important topic, special for specifically for us microscopists. When we are looking at a sample, for example, in this slide on the left side, we see our sample. It's a cross-sectional sample that was prepared, and we see several features. Some of the atoms sometimes there, sometimes are not there, and some of the features like lining next to the atoms, and sometimes it's also not very clear. So if you don't have other picture, we sometimes may or try to like explain what those features are. And a researcher can spend a little bit more time, or maybe hours of sample prep to make the image on the right side. So it's very important for us, if you have not good sample, when we're looking at it and try to analyze it, we come up with so many things in it, so many features, and it happened to me during my studies. I was trying to just make some hypothesis about the features that I have in my samples. I was coming up with so many theories, and then my advisor said, no, these are all artifacts. Even I remember my advisor told me that he spent 2 years on sample preparation, and he defended his PhD in 6 months. So it's a very important topic for microscopists. Sample preparation overview, I was just showing you a very short diagram that tries to simplify sample preparation for different types of solid samples. What I mean about solid is like they're not biological samples. So we can have bulk sample from the left. Bulk sample could be any pieces from a damaged turbine blade, or it could be thin films, or it could be like electronic chip in your computer, or it could be powders, any type of powders or nanoparticles that actually one of our viewers mentioned. And different types of sample preparation are required for each one of these. So if you look at this diagram, it shows that from left to right, you're actually getting less and less work to make the samples. For example, for bulk sample, we need to cut it, then make it smaller, then punch it, then grind it, then do electrochemical sample prep or other technique, or ion polishing. For powders, we just have it, we just put it in the solution, and we drop just a small drop of solution with a powder in it on the TM grid, and it's ready to go. I'm just covering 3 different type of sample preparation for solid materials. The first one is the edge polishing that uses a tripod. So these are the capabilities that we have at Columbia University. So imagine that we have a sample that has a surface which has some structured layers, for example, electronic sample that they deposited different types of layers like gold, platinum, and so on. And we are looking for atomic configuration at the interfaces or at the boundaries. So the way we prepare it, we attach a piece of sample on the tripod at the end of the tripod that I showed it here. And then what we do is very similar to we are sharpening a knife, and by several steps. And every step we are making it finer and finer. And then eventually at the very tip, we are making it electron transparent. The next technique is, so the previous technique is for cross-sectional samples. Dimple grinding is for surface observation, like a plan view. So if you have a sample which is like a flat sample, then we grind it with a whale. Then when it reaches to the level that it's almost transparent to light, we put it in the instrument that is called PIPS, Precision Ion Polishing System. And then we polish it with the argon, and the surface turns out to be very smooth and very polished and thin. The last technique that I would like to mention here that we are collaborating with CUNY, City University of New York, is the focus ion beam, or FIP. Probably some of our viewers know about this technique or may have used it. So instead of using a knife or a dimple grinder or something, we're using a very tiny, accurate ion beam to cut the sample and make some cuts or polish the sample. And when you look at the image on the right, you see that we can carve out very tiny and interesting features out of any type of sample, metal or solid or any hard samples. In the next video, I would like to show you a very quick overview how this technique works. So in this technique, we normally, since we are not only we are cutting the sample with the ion beam, we are also using ion beam to image the sample. So we need to protect the surface if we want to cut it. We protect the surface by a platinum, by depositing a platinum, in the range of like 1 or 2 to 3 micrometer. Then we use the same ion with a higher power, and then we carve out and make trenches, top and bottom of the sample. The next step is trying to take this part out of the sample. So look at this, that we are also, right now we are rotating the sample. And the sample is being cut from 3 sides, and it's attached from this side. And you can see that you need to take it out right now. Next, we are going to take it out by attaching a tiny needle. This needle is made of tungsten, and it's also very, very tiny at the tip. So you can see the needle is approaching the sample. Then we are going to attach it by the same platinum, and then we cut the other side, and then we are lifting it out. So you see how small it is. It is in the range of 20 micrometer. So handling this tiny sample is very challenging. So what we need to do is just put this sample on something else that we can hold it with, like tweezers. This is a TM grid. As you can see that we are preparing it for attaching this tiny sample. So the giant part of the TM FIP sample is 3 millimeter on this image, and that sample is around 10 to 15 micrometer. So we are putting it down, then we are going to attach the corners. Then the next step is cutting or making it thinner as possible. Thinning the sample. So we are using the same ion beam. This time we are using lower current and lower voltage. And we are looking up to bottom, and we are selecting the region of interest, and we can accurately cut a specific region of our interest. And we just continue till we see that the thickness of the sample is about or even lower than 100 nanometer. So look at this image. You see that the sample is getting brighter and brighter. It means that it's getting transparent to electrons. We can see the other side of it. This is a perfect sample for even higher resolution microscopy. Okay, go back to slides. Okay. This image shows an overview in 9 different images, from putting the platinum till the end to the thinning the sample, and the image on the left shows the instrument. So the next part, I'm going to briefly talk about one of the techniques that we use and we have for making biological samples. And this the picture on the right shows the ultramicrotome that makes slices in the range of nanometer size. And the way we do it is that there are several steps. So here we summarize it in 5 steps. It could be more or it could be less. But normally, most of the sample preparation for biological samples are start with fixation to stabilize the structure of the cell or the structure of the tissue. Then we need to dehydrate it or get rid of the water. Then we infiltrate it, replacing it with resin. Then we polymerize it in the oven or something that makes it hard. Like a glue that it gets hard. And then the last stage, when everything is ready, we can slice it with the ultramicrotome. The ultramicrotome, the diagram shows on the top right, and the slices that have been cut by the ultramicrotome shows on the bottom. It's cool that it's interesting that by different, if you cut it in different thicknesses, we see different colors. So as you can see how thin we can cut these samples. There are maps actually that shows that color versus thickness. So before continuing and going to the examples from some of the research studies at Columbia University at Nano Initiative, I would like to see if any of our users have any questions that I can answer right now. And then I continue.
Amir, it's Mike.
Sure.
There was a response to your question of why not using X-rays. Are you ready to talk about that yet?
Oh, okay. Now I'm okay. Yes. So the answer is correct because electrons, they're easier to control them. X-rays, they pass through most of the matters. So it's just it's a matter of controlling and focusing the electrons to a specific location of interest. If we could control X-rays and focus them in a specific location, actually we do have some X-ray microscope, but they are not as good as electron microscope. But yes, that's correct. Thank you, Max.
There was another question regarding your video. Actually, there was a request to be able to utilize that video in classroom to teach their students. Is that video, could that video become available?
Sure. The video, actually, I got it from the University of, I forgot, but I put a link down there, and you can watch it on YouTube, actually.
Fantastic.
Yes. So you can copy paste the link down there.
Bob, I think we're okay to go forward in the presentation, right?
Okay, sounds good.
Sure. So this part, I would like to talk briefly about some of the research projects. I brought here 5 examples. It's like a collaboration between several different departments: material science, mechanical engineering, physics, chemistry, and chemical engineering. And with my background, so I know a little bit of some of these, but I'm not very proficient on answering detailed question about these. So since you're collaborating with more than just these items, more than 20 or 30 people that have different depth of knowledge in different fields. So the first example, I would like to talk about the research that has been recently published that one of the students, a PhD student, he was very creative. He came up with the idea of using a very cheap coating on anything, like on glass or metal, and replacing the, absorbing the energy of sun and use the solar energy. So we have this technology for a long time, like 40 years or 50 years ago. But the thing is that that was expensive, and also the efficiency of those energy absorbers were not good. So he came up with the idea to use different type of powders, mainly of copper and zinc. That's a different compound. You can look at his paper. I put the link down there. The reason that they came to us was that to study why when they heat the sample to more than 200 centigrade, they don't see the same effect. So they're very interested to enhance the properties of their coating or powders at very high temperature. It's also important. So it was interesting that when they studied their powders at different temperatures, they saw a very interesting transition of zinc and copper from inside to outside, and it changes the properties of those particles, which makes the coating. And they were just looking for two answers, and the elemental mapping that shows the here and here, which shows that when they heat up the sample, zinc prefers to go inside and copper goes to outside, and it changes the properties of the powders very much. So they published their journal, their manuscript in the Advanced Materials, which is one of the high impact factor journals, and they actually it's featured on the back of this the cover page of this journal. The other research that I was collaborating with the team of mostly physicists. So my background is material science. So there were physicists and mechanical engineering that mostly there were also physics. And it was interesting that one of the researchers discovered that when they apply a little bit amount of voltage, a specific voltage, they see light that is coming from two graphene layers that are close to each other. And they were confused, and they were still it's ongoing research, and they showed me a video. I didn't bring it here, but there was some light that was coming from the connection between the two graphenes. So they published the results, the preliminary results in Nature, and but still the very good explanation was missing. So they came up with a very, to me, was very complicated physics explanation that was could be possible, but when we came and made a sample on TM, they were a little bit hesitant to accept that. When we look at the very high resolution image of the cross section of this sample, you see that at the middle, there is an area of confusion, which is carbon and silicon that are diffused together. And in this region, you see that we can clearly detect the graphene layer that are stacked on top of each other. But when we get here, it's a diffusion, and we observe that when we apply the electricity, it heats up maybe to 2000 Kelvin, and it diffuses everything here, and it produces a light. But still, we don't know a good, very good explanation yet. The other research project I would like to talk about is the two-dimensional materials that some of the researchers, so mostly two-dimensional materials are known for their good mechanical properties, but the researchers, Professor Hone and Ehrmann and Professor Shepard, they're interested on electronic and photonic properties of these samples. And they'd like to know how many defects these samples have. And what you see here is the high-resolution image, and you see the dots. Those are single atoms. And what we see here is like one tungsten atom is missing. The next slide is a collaboration with Barnard College. They were interested to make catalysts with titanium oxide that they were trying to deposit ruthenium on it. They were getting very mixed results on different particles, and they came up with the idea that some of the powders have an amorphous layer, like a shell, around each particle. These are particles that you see that actually they're pretty clear. So we did some imaging, and we saw that when we are looking at the fast Fourier transform of any of these high-resolution TM images, we see that there are root-type particles that are contributing to the efficiency of these particles. So they should come up with a better explanation. So these are some examples that when we are looking at the high-resolution image, we can understand what is actually happening. We see them. The other project is about the magnetic materials, the highly magnetic materials like iron, nickel, or iron palladium. They're showing very good magnetic properties, but the thing is that making them is still in large scale is a problem. So the reason that they were trying to make these samples because still most of the time magnetic materials are made of very rare earth elements that are expensive, and they're only found mostly in China. And they're trying to make cheaper magnetic materials. And this research was collaboration with the Northeastern University that were trying to see if they combine thermal treatment with mechanical treatment, they can get a better magnetic properties. You see the diffraction pattern that at specific mechanical or undeformed state at 505 annealing temperature, we get one of the good extra lattices which comes from a magnetic phase. This is almost my last slide that talks about ASTAR. ASTAR is a commercial name for crystal orientation mapping. And this is going to be one of the techniques that we are going to add on our system. And only few universities in the United States or around other countries have this technique. So if I simplify it in a short matter, it's just we are scanning our material, like this image. It's an image of the sample, just spot by spot, and we get diffraction pattern. And this diffraction pattern is more of a kinematic diffraction. I can explain it later if our viewers have questions. Then we are comparing this diffraction pattern with the library of diffraction, and we can guess the orientation of each grain, and we also can guess the phase. So we can make a color map as a combination of different phases and different orientation. For example, if you have nanoparticles in this size, like they're 20 nanometer, if you scan them by the ASTAR technique, you see that these particles are getting different colors depending on their color, depending on their orientation based on this color map. So I would like to thank everybody for listening. Thank you, Mike. Thank you, Nava. And if anybody have interested in our facility or they want to learn more, they can visit our website, or they can specifically email us. And I'm very happy to answer any questions.
Thank you very much, Amir. I had a question. Could you go back one slide, please, on the ASTAR technique? Is there a lot of computational stuff involved? I mean, is it a lot of processing power to take those diffraction patterns and convert them, or is it relatively straightforward?
Yeah, so the technique was, the theory was developed around 15 or 20 years ago, but the computation power at that time was not good enough. Yes, it needs a huge amount of, like, this image could be 10,000 different spots, and imagine that 10,000 diffraction pattern, you're going to, the software is going to analyze it one by one and give each spot at this map a different orientation and different phase. So when you get a map of this image, sometimes it comes in a 50 gigabyte of data. Wow. So, but nowadays it's not a problem. So since everything is getting bigger and like, yeah. But yeah, it requires a lot of time and computation.
One of my colleagues texted to me, he's on the webinar, could you go back to slide 45 and I'll tell you what he said. It's where he had that single vacancy. That's it.
Sure.
So we're actually looking at a single tungsten vacancy in that sea of selenium, I guess. That's amazing.
Right.
It's just simply amazing when, you know, we teach our students about, you know, ion implantation to put in impurities and semiconductor materials, and it's also obtuse, right? It's such a small number, but there it is. It's amazing. I've never seen an image like that. So.
Yeah, the other day my dad was asking me, do you really see atoms? I said, yes, kind of. You see a shadow. I said, how is it possible? I said, you do. You are able to see single atom in the image. Yes, we are able to do that.
Good. Well, thank you. He had to text me and said, look, I can't believe that slide 45. So I'd like to ask you, Amir, if you wouldn't mind to go on mute for a minute and to have Nava open up her microphone so I can ask her a follow-up question.
Sure.
Okay. Nava, here's the question for you. It came up earlier about remote operation, and you mentioned in your response that you don't have web-based operation, but can someone, a collaborator, send samples into you? Do you do that?
So it depends what. For electron microscopy, for instance, definitely we did some work for UCLA in the past, for some industrial companies that just send us samples. So it depends what. Cleanroom is a little more complicated because we are a little bit understaffed in the cleanroom. But there are definitely certain things that we can do, deposition, mass fabrication. So just send me specific questions and we'll definitely we'll try to help.
Well, that's good. Well, thank you. Now I wanted to thank you again, and both you and Amir, for the presentation today, showing all the capabilities that exist there at CNI. So thank you for that. One of our colleagues at a community college here in Arizona wants to use your focused ion beam to put their college logo on something. So it's not exactly a research project, but should be a lot of fun to do that. They like that Spartan image that you had there. So thank you both for that. So colleagues, let me take you forward. I'm going to jump to a couple of slides here. I'd like to remind you now, as we're coming to near the end of our webinar, about two things. The next webinar in our series, and here it comes, is protein-engineered nanomaterials. That's Friday, March 23rd, and you can register now by going to nanoforme.org/webinars, and as you know, we're always sending you announcements about webinars, but we're looking forward to the presentation by Dr. Montclair, protein-engineered nanomaterials. So join us for our next in the series in March. In fact, you can look at all of our upcoming webinars at the Nano4Me website and our collaborators at Arizona State University at the NCI Southwest Center. We collaborate on the production of many of the webinars together. So look forward to the upcoming ones through those web links. Now, as we come to the end of our presentation today, once again, we thank our two expert presenters and our moderator, Bob Ehrmann from Penn State. Thank you, Bob. Today, folks, I'm now going to turn on the final survey. It'll pop up in a new window on your computer. Presenters Nava and Amir, please don't take the survey or turn it off because that will accidentally shut it down. So here it is, folks. This officially ends our webinar presentation for today, and please go ahead and take the survey if you can. It should come up on your screen right now. Let's just check our system. Okay, I have to make a small adjustment to this. There it is. Okay, good. So you should see the survey. It's up now on our screens. Please go ahead and type that in. Colleagues, this officially ends our webinar today. I'm going back onto mute. I'll leave the system open so you can complete this very brief survey. Thank you again, Amir, Nava, and Bob. Goodbye, everyone.